So we'll wait for a few minutes and then we'll start the class. I'm sorry. So we'll wait for a few minutes and let students join and then we'll start the class. So I guess we'll start the class. Hello. So we'll start the class. Hello. Yeah. So we'll start the class. Let me turn on my video. So welcome to the last class of this course, which is titled as Sensor Technologies, Physics, Fabrication, and Circuits. This is the problem solving session of week 8, which is the last week. My name is Shomnath Bhattacharjee. I am pursuing my PhD from IIT Jodhpur. Electrical Engineering Department, and I will conduct this session. So this is some basic info about me. My name is Shomnath Bhattacharjee. As I have already told, I am pursuing my PhD in the Department of Electrical Engineering, IIT Jodhpur. My research interests are in the domain of flexible and organic transistors for neuromorphic computing. My educational background is that I have pursued my bachelor's degree with honors in physics. After that, I have completed my master's in electronics. So to know more about me, you can go into this details, and also you can connect with me through the social media link. As today is the last class, so I don't need to remind you about the class schedule and those things. So I'll conduct a summary class as well, and we'll just discuss about it later. So this is the basic course layout of our course. So the first week we have learned about the basics of sensors, where we have introduced sensors and basic what sensors are, what are actuators, how are they different, and those things. Then again in the next week we have learned about the parameters of the sensors, that how to characterize a sensor, if a sensor is particularly useful for your use case or not. Then we have learned about the physics of sensors, where we have learned about the capacitive type sensors, the thermal type sensors, and those things. After that, we have learned about the chemical and imperimetric sensors. Yeah, sorry. So then we have learned about the chemical and imperimetric sensors on the fourth week. Then again, we have learned about the optical and magnetic sensors and optomagnetic and electrostatic sensors as well. Further, we have learned about the fabrication and characterization of these sensors, how to deposit specific useful layers and pattern layers to your sensors. Then we have learned how to pattern those specific sensors. Finally, we'll learn how to utilize these sensors in a system and circuit. So this is our today's course overview, which is that we'll learn first about the signal conditioning circuits, then we'll learn about some basics of amplifiers, and then some filters. So first we need to know what is a signal conditioning circuit, right? So using basic blocks, we can learn that if a sensor is connected to an outside circuitry, we need a basic signal conditioning circuit or a middle block which will condition the signal we got from the sensor to be utilized in the circuit or the system directly. So this is called the signal condition circuit. There are several parts of the signal conditioning circuits. The most important one is the not the most important one, but the first one is the buffer or isolation block. Then we need to denoise our signal, so we need a filter block. And again, then if the signal is very low, so to utilize it using a like a real time system or something, we need a amplifier block. So these are the three kinds of signal conditioning circuits available for us, and the most important one is obviously a filter block and amplifier block. Although in some cases we definitely need a buffer and isolation block as well. So, sorry. So to learn more about these filters and amplifiers, I don't think we need to learn more about these buffer blocks, but still we'll learn about this. And let's move on to the next part. Right? Yes. So to learn about this signal conditioning circuits, we need to learn about some basic circuits, as already like discussed in the lectures as well. But still, we'll learn about this. That is voltage divider circuit. So what is a voltage divider or a potential divider circuit? If a voltage is applied to a resistance which is in series with a resistance like this, let's say this is the input voltage V in and this is the output voltage, we need to find out among these two resistances which are connected in a series format. So in this type cases, let's say if this R1 is a sensor, is a let's say a resistive type sensor. Okay, so we need to know what is the V output, that is output across this resistance R2, or let's say RS, that is the resistance of the sensors. So we need to found out what is the value of this. So if we consider there's a I current flowing through this line, so the value of I will be nothing but through this channel, the value of I will be V input by RT. So what is RT? RT is the total resistance of these two resistances. So I will be nothing but V in by R1 plus R2. To find out the voltage drop across these resistance. So the voltage drop across R2 will be nothing but the current flowing through it, that is I, or let's say we need to find out the V out. So I into R2. So it will be V in R2 by RT, or the total voltage, that is V in into R2 by R1 plus R2. So this is a basic voltage divider circuit, one of the most used circuits. And apart from this, there is another circuit which we need to know about this. So that is the Wheatstone bridge circuit. A Wheatstone bridge circuit is like this. There's a voltage source here. There will be resistances here attached with it. This is the voltage source or V in. Let's say this is R1 resistance, this is R2 resistance, this is R3, and this is R4. There's a terminal in between. So this is called as the Wheatstone bridge. And to get the bridge balanced, we can exchange any of the terminal to again a resistive type sensor. Begin with a resistive type sensor. Okay. So if let's say this point is your A point and this point is your B point. Okay. So if we consider this part as a separate voltage divider circuit and this part as a separate voltage divider circuit, we get to know that the value of VA is nothing but, if we are getting the value across R2, let's say this will be R2 by R1 plus R2 into V in, right? Similarly, if we consider VB at this point, so we are considering these 2 points, which will give us the value in these 2 points. Okay, so this will be nothing but R2 plus R3 plus R4 into V in. So we need the bridge to be in a in a condition where the bridge is balanced. So how to find out the balanced condition? The value of VAB should be zero in a balanced condition. Okay. So we need to find out the value of this. That is nothing but R2 into R1 plus R2 minus R4 into R3 plus R4, and everything will be this. So from this value, we can learn that is nothing but R2 multiplied by R3 and R4 minus R4 multiplied by R1 plus R2. From this, we can get the values of these two terms get cancelled out. So we'll find out that R2 R3 equals to R1 R4. From this, we can get the condition for balancing a bridge, that is nothing but R1 by R2 equals to R3 by R4. Okay, so this is the bridge balance condition. So why is it important? So as we can see that there are several resistances and those will be similarly affected by an environmental condition. So if a resistance R3 is replaced with, let's say, RS, that is the sensor resistance or a resistive touch sensor, the effect that happens with the RS will similarly happen with these things. So we can have a counter sensor which will negate the effects by the environment itself. Okay. So apart from this, let's see. So what are the advantages, right? So what I was saying that it will cancel out the effect of environmental parameters. So these things can be used as a buffer as well, or also as an amplifier, which is very simple in the concept as well. So can be used as buffer. So how can we use a voltage divider circuit as a buffer, right? So we have this value V output, which was equals to nothing but R2 by R1 plus R2 into V in. Let's say we have a specific V output, and depending on selecting this several values, we can control the amount of amplification happens there, and with the wine bridge, Wheatstone bridge as well. So now let's move on to something more deeper. That is one of the most required signal conditioning circuit. That is an amplifier. So the most common amplifier is op amp, which is the abbreviation of operational amplifier. So what is an operation amplifier? Operation amplifier, we can basically say it's a black box where no current passes through it, but still it works as an amplifier. So the basic block diagram looks like this. This is your basic op amp where you need to turn on this op amp by this control signals, and it has two terminals, that is the inverting terminal and the non-inverting terminal, and this is the output you will get from this. You will have two inputs, V1 and V2, and so this is the basic building block of and this is the inputs. Okay, so this is the basic building block of an op amp circuit, and with op amp the basic open loop gain, open loop gain. If it's like, let's say, A, then V output will be nothing but into the difference of the inputs. Okay, so as V2 was at the non-inverting terminal, V1 was at the inverting terminal, so it was like that. Okay, fine. Mm, wait a second. Yeah. So based on the configuration, there can be many use cases here. So one is the inverting mode amplifier. So the basic configuration is like this, where we put a resistance at the inverting terminal of the op amp, where there's no resistance at the non-inverting terminal. Okay. Here what happens that we put a resistance here, and if this is the output, and this is the input voltage applied. This is the basic structure of an inverting mode amplifier. So what happens here? Let's say there's a current I flowing through the circuits. Okay, that is, let's say I. So what will be the okay? So let's term out these things. Okay, so there's a basic concept of virtual grounding. So what happens in a virtual grounding? As the op-amp is a black box and no current passes through it, so we need to know what is virtual grounding. So virtual grounding is that both of these terminals will have same amount of current. Okay, so let's see if the current is I, which was passing through it, it will be V in by I1. Okay, so what's happening through this is the current which is passing through the through this channel. Okay, and similarly minus I will be nothing but V out by R2. Okay. Similarly, there will be another flow of this because let's say both of them are here. Okay. So what will be the value of V out? The value of V out will be minus R2 by R1 into V in, where we are just equaling the values of I. So as we can see that if it's a gain, so the gain factor is nothing but R2 by R1. Okay. So there's a negative term, so that's why we are saying this as an inverting amplifier. So what I'll do, I'll just modify this part directly. So in the like non-inverting mode of this transistor, we'll just connect. No, sorry, we'll just connect a direct input to the positive one, that is the non-inverting terminal. The output we'll get from here. We'll just put a resistance that will go to the ground line, and there will be another resistance that will be here. So in most of the cases, this R1 works as a feedback line. That's why we say it as the feedback resistor, or we can also nomenclature it as an RF as well. So here, if it's R1 and R2, so what will happen that if the current is passing through it, so the value of I will be this time V out by R1 plus R2, as it will pass through both the lines, right? So the value of I will be V out by R1 plus R2, and similarly the value of I will be V in by R1. So we can write it down as V out, sorry, so V out equals to 1 plus R2 by R1 into V in. So as this term is clearly in a like a positive state, also this is called as the non-inverting terminal. Okay, so now we'll work with the adder or summing circuit. Okay, so in a similar manner where we were working with a non-inverting circuit, we'll just put several resistors like this. So all these lines will come at the same point, and it will go directly to the non-inverting terminal here. So it is the non-inverting amplifier base where we'll use R1, R2 and R3 three resistors, where this will be V1, V2 and V3. So we'll have another resistance which is known as the feedback resistor, and this is the V outline. Okay, so similarly using that we can find out that RF by R1 plus RF by R2 plus RF by RG equals to V1 here, V2 here, and V3 here. Okay. So if in this case, let's say RF, um, otherwise, like RF is like same for all, we can see that same for all, right? And R1 equals to R2 equals to R3, let's say. So what will happen with this equation is V out will be minus of, and these factors will be there anyways. So these factors will be V1 plus V2 plus V3 multiplied by RF by R1. So as we have already told that RF by R1 is our gain factor, so it will be nothing but with the specific gain we'll get the summation of our given input values. Okay. Yeah. So we'll have a few minutes break and then we'll start again. Yeah, so we'll start again. Yeah. So after this kind of a oh sorry, I forgot to turn on my video. Yeah. So after this kind of amplifiers, one of the most important amplifier is an instrumentation amplifier. Instrumentation amplifier. So what's an instrumentation amplifier? The IC808422 is an instrumentation amplifier where we can see it has two control signals. Okay, this is plus Vs and minus Vs. This is the output one. This is the non-inverting terminal and inverting terminal. This is the control signal or the signal voltage, and this is the output. This is the reference values. So this is a basic what do I say, like AD8422 structure, and through this you can see this structure is nothing but an voltage follower circuit. Okay. Similarly, this structure is nothing but another voltage follower circuit. So this first block, maybe it will be better to use this thing. So this first block works as an buffer. Similarly, the second block, this one, it is a basic configuration where we can write it like this. So this is nothing but this, where there's a feedback, that is R3 here, and through this we can see there is a resistance there. So here, and there's also a line here. So let's eliminate those. So through this we can see that it is nothing but an differential amplifier circuit. Okay, so in an instrumentation amplifier there is a buffer part at the first, and then there is a differential amplifier part. So this is the most used amplifier, where we can use it as a buffer and also as an amplifier at the same time. Okay, so we'll move on to the next part, that is the our filters. So there are several kind of filters. The most common ones are LPF, that is the low pass filter. So we are not gonna learn about the like circuits, but we'll learn about the basic output we need from a filter. Where if we know that there are, let's first draw this, and we'll then explain about this. So this is a general characteristics of a low pass filter. So what happens that if we know that our signal is within this range only, and after that if there is anything found out in the output region, sorry, anything found out in the output region, let me just clear this first. After that, if anything is found out here in this region, we should just cancel it out. So if we know that the noise is of like with higher frequency margins, we need a low pass filter where we will just pass only the signal which is inside the lower frequency region, where the noise is in the more in the higher frequency region. Apart from this, there is also HPF, which is nothing but the counterpart of a low pass filter, that is the high pass filter. So if we know that our signal belongs to the higher frequency region but not in the lower frequency region, this is called as the high pass filter. So this will be the higher cutoff frequency after which the signal shouldn't pass through this filter, and this is the lower cutoff frequency where after this the after this only the signal after this with the with the frequency above this point, that is the FL, the signal should pass. So this is the high pass filter. Apart from this, the high pass filter, there is the BPF, that is the band pass filter. What is a band pass filter? So if we know that our signal just lies within a specific like predefined range, let's say, so we know that it belongs to this specific frequency, we'll just negate out the excess noise within this region, and this will be the band pass filter. Similarly, there will be another counterpart that is known as the BRF, or the band reject filter. So what will it do? That if we know that our signal doesn't belong to this specific region, we'll just negate that portion out. So this is known as a band reject filter. So from signals from the frequency range F1 to F2 is rejected, while signals from 0 to F1 is rejected, and F2 to infinite is rejected. Whereas similarly in high pass filter, signals from 0 to Fn is rejected, while in low pass filter, signals from Fh to infinity is getting rejected. So there is a basic basic functioning of an filter. So this was the basic things we have to learn today. Apart from this, we'll just move on to some questions and then we'll discuss those questions. So as we have already learned about the Wheatstone bridge, so Wheatstone bridge, a DC bridge, AC bridge, high voltage bridge, or power dissipation bridge. Which one will be the correct one? So let's draw the structure again. So if there is an V input in the structure, the bridge looks like this. Here is a resistor. Let's mark it out. Or maybe through a marker, maybe it will be better. Here is a resistor. Here is a resistor. Here is a sorry. Here is a resistor, and here is a resistor. Okay. So there are four resistors in each of the arms, and through this we need to know the current. Okay. So as we have already told you that V input is a DC voltage. It can't be working in a AC voltage. So it is not obviously an AC bridge. Then it is obviously a DC bridge. Okay. So will high voltage work? No, it won't work because there are several circuitries that is only resistors. So high voltage bridge it is also wrong, and there is no power dissipation as such. So this is not a power dissipation bridge as well. So it is nothing but a DC bridge. Maybe I can explain this a bit. So if there is a resistance like this, so we can simplify the Wheatstone bridge as like this. Okay, so from this point to this point, there is a voltage of V in, and if let's say this one is our sensor, that is RS, and apart from that, this one is R1, this one is R2, and this one is R3. So in balanced condition, it will be nothing but R1 equals to R2 by R3 by RS. This is in the balanced condition. So we need a DC voltage to cancel out, and then we'll find out only based on the resistor what is the with respect to like the environmental factors. We are getting those factors, and we are getting only the value of this sensor. Okay. So moving on to the next question, that is this one. Okay. So a thermistor of 10 kilo ohm written on it is placed in a voltage divider circuit. Okay, this is the thermistor we are talking about. So at first we know that our thermistor is 10 kilo ohms. Okay, so it is placed in a voltage divider circuit below. If the input voltage is V, so they have already told that the input voltage is 5 volts. Okay, the voltage across the thermistor will be something. So the other value of resistor, that is the R1, is nothing but 30 kilo ohms. The voltage across the thermistor, that is the V thermistor, will be what? The V thermistor will be nothing but R, that is the R thermistor, by R1 plus R thermistor, or R thermistor is nothing but 10 divided by 30 plus 10 multiplied by the V in into 5. So this is 50 by 40, which is nothing but 1.25 in volts. And this will be also in volts. Here is the value of this. I'm sorry, just 27. Yeah. So similarly, that's another problem. So if there are two thermistors that are placed in a voltage divider circuit shown in here. So at first we know that the input voltage V in is 20 volts and the output voltage V out is 1.818 volts. Okay, and the resistance of the thermistor is in kilo ohms. So we need to determine the resistance of the thermistor, that is our question mark mainly. And we also know from the curve that is R1 is nothing but 10 kilo ohms. So based on the voltage divider circuit, we know that V out is nothing but R of the thermistor by divided by R1 plus R of the thermistor multiplied by V in. So if we put it here, so it will be 1.818 equals to R of the thermistor by 10 plus R of the thermistor. And we'll found out this in the units of kilo ohms. So that's why we can remove the units from here. That is like that will be in the kilo ohms range, right? And it will be multiplied with 20 volts. So to find out, we can know that R of the thermistor into 1.818 equals to 20 R of the thermistor. Okay. From here, we'll just move on to here, and the values will be 18.18 plus 1.818 into R of the thermistor equals to 20 into R of the thermistor. Now, if we just calculate this, this will be nothing but just 20 minus 1.818. So it is nothing but 18.182 R of the thermistor. 18.81 to R of the thermistor equals to 18.18. So R of the thermistor will be nothing but 18.18 by 18.182. So this will be 0.99989, or let's say 1 kilo ohms. Okay, so this will be the value of this resistance. Yeah, so this will be the value of this. This resistance is 1 kilo ohms. Okay, we'll move on to the next question. And after this question, I'll take a break and for 2 minutes, and you can just try to solve it. Okay. So a temperature sensor is placed at a specific position in a voltage divider circuit with an input voltage of, that is V input of 20 volts. The variation in resistance for minimum temperature and the maximum temperature is shown in the curve. So we can get information from this curve as well. Find out the output voltage across the sensor for minimum temperature. So we need to find out V out at minimum T and V out at maximum T. So what will be the value here and what will be the value here? Okay. Yeah, so I'll solve the problem and then let's so yeah, how to solve this, right? So first we need to know what is the minimum temperature here. So clearly it's visible from here, that is 10 degrees C. Okay. And what is the maximum temperature? That is 80 degrees C. Maximum temperature, that is 80 degrees C. And corresponding to that temperature, we also need to know what is the temperature of the sensor. So corresponding to 10 degrees centigrade, its value is 20 K. So at the minimum temperature, the resistance is also minimum, which will be 20 kilo ohms. Okay, and corresponding to that, the maximum temperature at this value will be sorry, the maximum resistance at the maximum temperature will be nothing but 200 kilo ohms. Okay, so how to calculate the values, right? So at the value of minimum temperature, V output will be nothing but resistance of the sensor divided by R1 plus R of the sensor multiplied by V in. Okay, the value will be 20 cross 20 by 20 plus 20, that is nothing but 400 by 40, so that is nothing but 10 volts. Okay, and to further calculate the next part, at the maximum T, max T, what will be the value of this V output at max T? Okay, so it will be the same formula, right? R sensor divided by R1 plus R sensor as well. So the formula in this case will be 200 cross 20 by 20 plus 200 into V in. That is nothing but 18.18 volts. Okay, so at the maximum temperature, the maximum voltage will be 18.18, while at the minimum temperature, the voltage will be the less. So your V output will be in the range of 10 volts to your 18.8 sorry 18.18 volts. Okay, so this will be the value. We move on to the next question, that is a thermistor is connected at one of the arms of an Wheatstone bridge. So why should we move to that one? So based on the sensor temperature, there was a variation in the sensor resistance in those cases. So to avoid those things, we need to move on to an Wheatstone bridge structure. So based on the Wheatstone bridge structure here, if the bridge is balanced, what is the resistance value of the thermistor? So we know these are the values we know, that is V in is 20 volts, R1 is 100 kilo ohms, R2 is 200 kilo ohms, R3 is 50 kilo ohms, and R4 is RT. That is the temperature as a resistance of the thermistor. So we need to know this value. So like we already know, okay, at this case, so as like we already know the bridge is balanced, so as the bridge is in balanced condition, we know that this will be the balanced condition, R1 by R2 equals to R3 by RT. Okay, so we know the value of R1, that is 100k, divided by R2, that is 200k, R3 is 50k, while RT is this. So the value of RT will be how much? That will be 100K as well. Okay, the value will be 100K as well. We'll move on to the next question, that is in the circuit below. Yeah. So in the circuit below, if the temperature of the thermistor changes from 25 degree, that is temperature is variable temperature, that is from 25 degrees C to 30 degrees C. Okay. On application of heat, and then resistance changes from 80 kilo ohms to 100 kilo ohms. So there is a change in resistance, that is from 80 kilo ohms to 100 kilo ohms. Okay, so this is our change in resistance and this is our change in temperature. So in the previous question, what we have done, we have calculated these values from the curve itself, while here we have already got the data directly from the question itself. Okay, and now what happens that due to this value there is a change in R3. R3 increases by plus 5 kilo ohms. Okay, so we need to know what is the value of R3 here. We need to determine this value. Okay, so this is the value. So at first, at the let's say at the initial condition. So what was the value of sorry? So at the initial condition, what was the value of RT? So the value of RT was nothing but 80 kilo ohms. Okay, so this was the value of RT as given directly from the equation. Okay, and now so we know the balance condition is nothing but the balance condition is R1 by R2 equals to R3 by RT. Okay, so based on this we know that R1 by R2 equals to nothing but R3 by 80 kilo ohms. Okay, now so this condition B, where it's in the final condition. So what was the value at the final condition? At the final condition, RT was 100 kilo ohms. Okay, so similarly, with respect to the balance condition, this will be similar. R1 by R2 equals to R3 by RT. Now, so R1 by R2 will be how much? R3 plus 5 by 100. Okay, so why is it like this? Because we already know with the increase in so with the increase in temperature, R3 increases by 5 kilo ohms and RT changes to 100 kilo ohm range. Okay, so we have an equation like this and we have a condition like this. So using both the conditions, we can derive these values directly. So by comparing both, but we get to know that it is R3 by 80 equals to R3 plus 5 by 100. Okay, so the value of R3 is 100 minus 20 and this will be 20. Okay, so this is nothing but 20 kilo ohms. The value of RC will be 20 kilo ohms. Okay, so is it correct or not? So it will be 20. Yeah, it will be 20. So value of R3 when the bridge is balanced, it will be 20 kilo ohms. Okay, so move on to the next question. So in an inverting amplifier configuration of an op-amp, a thermistor of resistance 5 kilo ohm is placed in the feedback path. So from this we get to know RF equals to R thermistor equals to 5 kilo ohm. Okay, shown the value of the output voltage at the inverting amplifier. So we need to find out the value of VO out. So I'll give you like 2 minutes and try to answer this and how to calculate this as well. So as per the inverting configuration, I should give you a hint. Inverting mode of an amplifier or like using an op amp obviously, the value is nothing but V output equals to minus of RF by R1 multiplied by Vn. Okay, so this is the basic equation of this. So from this we get to know that V out is equals to minus of 5 kilo ohm divided by 10 kilo ohm from the figure into multiplied by V in, that is 80 volts. Okay, from this. So this will be how much? This will be minus 40 volts. So like by giving an input of 80 volts, we get an output of approximately minus 40 volts. So as it is an inverting amplifier, so we'll get anyways 40 volts. So what will be the so this was the answer. Although we need to also get the values of our gain. So what will be the inverting amplifier gain? So what is the gain of this inverting amplifier? So this is nothing but minus 40 by 80, that is minus 0.5. This is the inverting amplifier gain. Okay, now let's move on to the next question. Let's change the color of the sink. Determine the output voltage for the given amplifier shown in this figure, which is here. So this is another like criterion we have already been given, that is V1 equals to minus V2, which is equals to 1 volt. So clearly V1 has a value of 1 volts while V2 has a value of minus 1 volts. Okay, so here we are just giving 1 volts of voltage to this terminal while we are giving 1 volts of minus 1 volts of voltage to this terminal. Okay, so we need to like get this value, that is V output. So this structure is very similar to some structures like from this part you can say this is an inverting structure where we have an resistance here and resistance here, and if this is an op amp, this should have been to the ground. Okay, so this was the basic structure of an inverting amplifier, while a non-inverting amplifier was like this. So this was a non-inverting amplifier. Okay, okay. So calculate the value of this amplifier. I'll give you 2 minutes and then try to do this. And okay, so after 1 minute, I will give you a clue. Maybe you guys can also write it in the like chat box as well if you have any issue with the mic also. And for this purpose, I'll also mark this. This okay. And also for the sake of clarity, there will be this terminals as well. Okay, try to answer this. Maybe I'll give you a hint. So let's say, what happened? Let's say this point is A, and let's say this point is B. Okay, let's think of this as like this. So with the concept of virtual grounding, think of it. Okay, so the basic concept should be like you to calculate VA and then to calculate VB and then try to equal them. So for my sake, like I will just remove these things for now. Okay, maybe let's delete this one as well and we'll just write it here. So V1 is 1 volts while V2 is minus 1 volts. Okay, so maybe I'll just explain this. So let us do what let us maybe I'll write it down. Let us take 2 points E and P. So as we have already taken that I was taking, then the voltages are V and B. Okay, so we're taking that at this point the voltage is VA, while at this point the voltage is VB. So as I have already discussed, right? So we'll use the basic KCL. So by KCL, okay. So by KCL, what we'll do that we'll just get the value of through a closed loop, right? Okay. So so what will be the values here? So like 100 cross 100 multiplied by VA will be equals to 100 cross V1 plus 100 cross V out. So is it correct? Yeah. Okay. So the value of VA will be 100 cross V1 plus 100 cross V out divided by 100 cross 100. Okay. So this is the basic case. So we can directly write it out like V1 plus V out divided by 2. Okay. Now, similarly, that was for the first loop, and now for the second loop, we'll get the values. So the values will be similarly like 20 plus 20 multiplied into VB equals to 20 into V2. Well, there will be 0 because there's a ground line here. So it will be 0 into 20. Okay. So VB will be 20 into V out divided by 20 plus 20. So this is nothing but V2 by 2. Okay. So by equating both of these two, I'll use a different color maybe. Yeah. So using the concept of virtual grounding, so what we'll do, we'll just equate these two. So as we know that if there is a V and VB, so the concept of virtual grounding is VA equals to VB, right? So what we'll do, we'll just equate these two. So V1 plus V out divided by 2 is nothing but V2 by 2. Okay. So we'll found out V out equals to 2 into V2 by 2 minus V1 by 2. It is correct, right? Yeah. Sorry. I'll just put it here. Okay. So, I'll just maybe write it again. Okay. Yeah. So, V out into 2 is there, right? So, V out is 1 V out into 2. So, there will be 2 multiplied by V2 by 2 minus V1 by 2. Okay. Or else we can write it as V out equals to V2 minus V1. Okay. So from here we know that V2 is minus 1 and V1 is 1, right? So similarly the value will be minus 2 volts. So the value of V out is nothing but minus 2 volt. This is 2 volt in minus. Okay. So if we put in this circuit that V1 equals to 1 volts and V2 equals to minus 1 volt, the value of V out will be nothing but minus 2 volt. Okay. Moving on to the next question, that is this. Okay. So balance condition of a Wheatstone bridge is obtained when there is no flow of current through the galvanometer. So galvanometer is here at this configuration. Here that there is a galvanometer. Okay. So there is no current through this. Obviously, as we were aiming to be AB equals to 0, that is this is the A point and this is the B point. If there is no voltage in between it, so the current at IG should also be 0, right? So this one is the true. Then we'll move on to the second one, that is the galvanometer reading is maximum. So they are saying that this is max. So this can't be true, right? So this one is not true. Then the next one is there is a current flow through the galvanometer. So they are saying that IG is not equals to 0. So this won't be possible with VAB equals to 0, right? So this is also 0. There is a voltage difference between galvanometer terminals. So they are saying VAB is not equals to 0. So this is also wrong. So to explain this one is saying that VAB not equals to 0. That is wrong. This one is saying that IG not equals to 0. That is also wrong. They are saying IG is max. So it can be like very high value. So this is also wrong. While this one is saying IG equals to 0. So this one is a true one, right? So we'll move on to the next question. Okay, the final one. So determine the flowing current through the 2 ohm resistance. So through this resistance, we need to get the values. Okay. So first, what we need to like draw the circuit like this. sorry for the this bad drawing. So we can essentially write the circuit it like this. So this is 1K, this is 3K, this is 12 volts, this is 2K, and this is 6K. Sorry, this is 10K. Okay, so this is a basic circuit. So I'll give you 2 minutes and then you can try to answer this. Yeah, so any answers? No. Okay. So maybe I'll simplify this. So if we need the Wheatstone bridge to be in a balanced condition, sorry, I don't know what's happening. Yeah. So what I was saying that to bring this Wheatstone bridge to a balanced condition, we know the condition is R1 by R2 equals to R3 by R4, right? So here this one is R1, this one is R2, this one is R3, and this one is R4. Okay. So let's check if the bridge is in balanced condition or not. So R1 was 1 kilo ohms and R2 was 2 kilo ohms. So the value is 0.5, and similarly R3 is 3 kilo ohms and this is 6 kilo ohms. So both of them are giving us zero point 0.5. So both are in the same. So the bridge is in balanced condition. Okay. So as the bridge is in balanced condition, so let's say this point was A and this point was B. So there won't be any current flowing through this. So this is a fake resistor, let's say. Okay. So there won't be any current flow through this one because the voltage drop across this will be VAB is 0 and I through 10 is also 0. So there is no resistance at all. Okay. Now the circuit is then open circuit. Okay. As this one is an open circuit then. Okay. So the current through this 2 kilo ohm resistance is so we'll use the Ohm's law. So through Ohm's law we can know that this current is nothing but this, right? So this one is R2, this one is R1, and this one is the V1 or the, like, let's say V in. Okay, V in. Okay, so this is V in R2 and R1. So the we are I'm just giving confusing explanations. Just remove this. Okay, so we need to get the value of I at R2, that is nothing but V at R2 and R1 plus R2. So this one is V is 12 volts divided by 1 plus 2 kilo ohms. Okay, so this is 4 milliamps. Okay, so this will be the value value of IR2. So this is the answer we require. So today in this class we have learned about this like Wheatstone bridge problems, and we have learned more about the op-amp problems where we just delve deeper into this kind of a things. Then there was Wheatstone bridge problems, many problems, and then we have learned about the voltage divider circuit problems. So these are the basic problems we know, and then apart from that, we have learned about the filters. As we have not delved deeper into this kind of filter structures. So that's why I have omitted those kind of problems from here. And this is the basic like most used amplifier circuit. That is sorry, I haven't written the name even. So it is trans. Sorry. This is a sorry. Instrumentation amplifier. Oh, sorry, I have written this. Okay, never mind. Okay. So we have learned about the summing circuits where we have used it for adder circuits and summing circuits. Then we have learned how to use the amplifiers in inverting mode and non-inverting mode, and how to utilize those in differential circuit, how to utilize those in a buffer circuit. So how to use it as a buffer, right? So let's take the example from this circuit directly, right? So here we had this value. Okay, so we'll just change the values, and like we can't use it as a direct buffer, but to use it as a direct buffer, like here you need to just if R1 and R2 is same, then it will be 2 times this, so the value of gain will be 2. Well, in this case the value of gain will be -1. So like we can't directly use it, but like utilizing these circuits we can use it as an buffer, and I guess there is an buffer circuit here. Yes, so this is nothing but an voltage follower buffer circuit, right? So as there is no resistance in the front part, so sorry. Oops. Yeah. So as there is no resistance in the front part, right? So what we can do here? So through this equation, we can directly write for buffer. What we'll do that V output will be this 1 plus R2 by R1 into Vin, right? So now in that case, there was no R1 circuit. So it will look like this 1 plus R2 by 0. Sorry. So not like this, but it will negate the effects. Obviously, we can't put it like tightly like here, but it's like, let's say, like it is not correct to put it like this, but as there is no like resistance, so it will be like this and it will be like this. Okay, so there will be only the term that is here, so that is the voltage follower circuit that will follow the voltages. Okay, apart from this, like we have learned about the Whitstone region voltage divider, we have extensively like done some problems from this. This is the signal conditioning circuits, and so this is it. So if you have any questions, please like let me know. I'll try to answer those. Otherwise, we'll conclude our session for this. If anyone have any question, please like let me know. Or you can write it in the chat box as well if you want. So if there is no question, then we'll conclude today's session. There will be a summary session on Wednesday, I guess, from 5. So let us see. Okay, fine. Thank you.